Good afternoon and welcome to Codebase Alpha episode 74, and this is an extra stream really because I'm not able to stream on my usual slot on a Wednesday at this time. I'm a bit late actually starting because I had a few issues authenticating OBS into Twitch. I had to kind of fiddle around with the settings, and eventually I managed to find that if I changed the server that I was connected to, it authenticated correctly. So I don't know if the server I normally connect to was having an issue, but it was giving a very strange JSON error message. So I've kind of sorted that out, and eventually here we are about 20 minutes late starting. So it won't be a very long stream today, but I thought we'd do a little stream just to kind of catch up with the Z80 emulator project and where I'm at. So I've been a bit distracted really from it because it's quite a lot of work to do, adding all the operation codes. There's many hundreds of them. So I got kind of slightly distracted and decided to do some other things with the emulator. So the first thing that I built over the weekend was a disassembler. So this is where we take the machine code and we convert it back into assembly language and display it. And I'll show you that. And I've also started work on a WPF-based debugger. It's kind of graphic debugger. We'll have a look at that and maybe do a bit of coding on that. I think it's probably the plan for today's say truncated stream, especially as I started late. Okay, so let's pop over into the code and have a look what I did over the weekend. So we're in the Z80 class here, the main partial class file, Z80.sc, and towards the bottom here we've got a couple of new methods. Firstly, we have where is it? Where we have this disassemble method, and what we're doing here is basically we're taking a start and end address, and what we're going to do is run through that memory, and we're going to find any instructions a part of that memory and say convert them from the machine code back into assembly language. So that's what this disassemble instruction does here. We're passing in address, and we're getting back this tuple of the address that we passed in, basically the instruction as a string. So this is the string version of the instruction, and then the next address that we're going to process, because obviously some instructions take up 1 byte, 2 bytes or 3 bytes, and then they may have operands as well, so we don't really know how many bytes they're going to kind of consume. So this next address is going to give me back the next starting address for an instruction. And then if we go and have a look at the disassemble instruction, now this is ripe for some refactoring because this switch statement we got here is very, very similar to the switch statement we got up for the actually fetching the next instruction and processing it, executing the instruction. So I'm going to be coming back at some point and doing some refactoring to combine these two switch statements into one, and it should be fairly easy to do, but I haven't bothered at the moment because the idea was to get the disassembler running, and I can test that separately. Obviously now I've got some tests that support the disassembly as well, then as I do the refactoring I've got that safety net, and that's the kind of whole point of having the unit tests really. So in this piece of code what we're doing is we're taking in the start address, we're reading that from the bus out of memory, and then we're kind of looping, we're going through this switch statement to try and find out what the instruction is and which instruction table to get the information from. So if it starts with CB, we're going to the CB instruction table and getting that, CD, etc, etc. And if we don't find any of those combinations of the multi-bytes, then we get it from the root instruction table. We can then grab the mnemonic from there, and then we can go and process it for operands. And how I'm figuring out how many operands there are and where they are in memory, then I'm using the addressing mode. We only need to look at addressing mode 1 in this case. So far at least all the commands we've got. So if it's immediate mode, then the very next byte is a 8-bit operand. If it's IMS, which is immediate signed, then once again it's the very next byte is an operand, but that's to be interpreted as a signed byte and not an unsigned byte, as it would be with the IMM addressing mode. And you can see what we're doing there is we're looking at we kind of read that byte from memory, and then we kind of replace. We kind of we manipulate the mnemonic string. If it had plus D in it, we change it to plus or minus whatever the value is, and if it was an E, which is what we use for the relative jumps, then we do a slightly different replacement. And if the addressing mode was IMX, which is immediate extended, then we get the next 2 bytes, and that forms a 16-bit, either an address or a 16-bit operand. And you can see we take the low byte first and the high byte, and then we combine them. And this is because the Z80 is little endian, so it uses it kind of reverses the byte, a low byte and a high byte. Excuse me. So get rid of that blank space there. So we do have some tests to support this. So if I pop over to our test project, we've got a disassembler should set of tests. There's 2 tests in here at the moment. So what I've got is we kind of developed the arithmetic hex file and the multiplication hex file. I think on the last stream we developed the multiplication routine, and what I've done is basically created an expected disassembly as the dictionary here. I load in the machine code using our fake it easy fake here, which is going to read that kind of memory, fake memory, and then we disassemble it, and then we say, are they the same? And the same here with the multiplication, which has got slightly more variety. And this is just straight loads and adds and subtractions, and this one here has got it's got some relative jumps, and these relative jumps are quite interesting because the assembler actually adjusts for the fact that the program count has actually been incremented twice. So even though we've got +3 here, the actual value which goes into the machine code would be actually +1. And if it was a negative number, it would be two more negative, because the program count has already moved on. I think we explained all that last time. Okay, so we can run these tests, and you'll see that our disassembler indeed does function correctly. Execute those. Right, there we are. So we can see that this disassembler has given you the exact results we expected. And this text here is basically what we wrote in our assembler last stream. In fact, the only difference is I'm kind of adopted the convention of marking hex numbers with an ampersand in front of them rather than a lowercase h at the end, and I've kind of done that for compatibility with the assembly language display that the Amstrad CPC uses on our WinApe emulator that we've got kind of as a kind of guide to what the disassembly should look like. So just trying to make them compatible with it, so it's easy for me to generate assembly language, turn it into machine code, and then to reverse the process of my disassembler and make sure it's all looking okay. So that's the disassembler, and I'm not using that anywhere yet. That's really part of the debugger. You'll notice we also have now a extra project here. This is the smb.z80.debugger, and this is a WPF application. I'll just run it up so you can see what it looks like at the moment, and then we'll go through what the actual code looks like. So it doesn't do much at the moment. So we have a window here. We've got a set of buttons at the bottom here. So we've got a button which allows us to step through the code, and the code effectively starts where the program counters pointing, and I've defaulted the program counter up here to point at 8000 hex, which in kind of an Amstrad CPC is a safe place to start user programs. We can start our programs anywhere we want in our emulator so far, because we haven't got a monitor or an operating system or basic in memory actually set up, so we can go anywhere. But 8000 seems a reasonable place to start. And I can now use the load button here to load in some machine code. So if I load in, say, for example, the multiplication program here, so it's going to look for hex files. This is the files in the Intel hex format. I can load that in. And down the bottom here, we've got a memory map. So this is simply there's 15 bytes per row, and we can then scroll down and look at the memory that we've got loaded. And if I go down to 8000 hex, oops, I have to make these windows a bit larger, but they're okay at the moment. So we want 8000. There we go, getting there. And we should see our program there. So there's the actual program that we've loaded in. So there's not an awful lot to it. There's just a couple of rows of the machine code, and then we've got this a disassemble here, which we're going to wire up at some point, which will just disassemble all the code between the from and to addresses. And we can, the single step button here now will actually step through our code and execute it. And we can see that it's doing that because the program counter will jump up. It won't go up in ones because this machine code is multi-byte operations and operands in there as well. If I press step, we go to 8003, 8005, and we're actually executing that program at the moment, but we're not seeing any effects because I haven't completed the GUI. So that's basically how that's working. And what does the code actually look like? Well, let's have a look at that. So we're using T4 template to actually generate the view model. So if you followed my streams before, with Morton we did a couple of streams on T4 templates, and back in the synthesizer project that we did, WPF-based synthesizer, we used T4 templates as well, which Morton kind of brought in to the project. So thought I'd use those again. The T4 template is basically all I do is I kind of list out the bind properties and any commands in here, and when I save this file it generates the partial class and the partial methods which support those properties, those bindings and those commands. So currently we've got the 3 commands: step, load and disassemble, and we've got four properties. So we've got the program counter, which you saw on the screen as PC, and the disassemble from and the disassemble to text boxes, and then we've got that memory map, which is a dictionary of string and string, so that's why it's linked in there. The dictionary, it's safe for me to use a dictionary in this case rather than some kind of observable collection, because I'm not actually allowing you to change any values in memory from the debugger. The things we're going to change are going to be the values in the registers, particularly in the flags. And we've only got program counter at the moment, and we can go and change that. I think it will work appropriately. Okay, so that's our T4 template, and we'll come across that again in a moment. We've got our XAML files. So what I've done here is I've broken our UI up into kind of basically 5 areas. We've got this area here, which is going to be where the disassembly happens. At the moment it's going to be an address and the instruction, but we probably want more. The disassembler probably needs to do a bit more than it does at the moment. Currently it just gives you the kind of the mnemonic and the operands, but we might want it to show the machine code and also the ASCII interpretation of the machine code, but we haven't done that yet. This is the memory map, which you've already seen. We've got our command, a panel here with currently just the 3 buttons and 2 text boxes, and then over here we've got the CPU status in this area, currently only the program counter being shown, and then in this area down at the bottom here we're going to have the stack, so we can see values being pushed and popped onto and off the stack. I've created for this area, and here, I've created user controls, just in an effort to try and keep the XAML file small, because my experience with XAML on the synthesizer project was it started to become very difficult to use because it was so large. So I've decided I'll split it in user controls. There's something, I'm not an expert by any means in WPF. I'm very much a beginner, so I'm open to pull requests to improve all this kind of code, and it'd be very helpful if people want to contribute in that fashion. So here's our disassembler memory of a control panel, and then the CPU status user control goes here. If we go and look at one of those, for example, I don't know, we'll look at the memory map, then it's basically a data grid, and we've got the binding here to our memory dictionary. We've turned auto generation of columns off, and then we define our own columns, and you can see they're read-only columns, and we bind the key and the value each column. Okay, so that's the basis of the front end. Our view model. So the view model, as I said, is a partial class. So part of it is being generated from our T4 template, and the other part is being built manually here. So we're taking advantage of partial methods. If you've not come across partial methods, this is a partial method. So we put kind of the custom code in here, the customizations that we want to do, and the boilerplate code is being created for us by the T4 template. So all we need to do is to kind of build what's different about our property, which is quite good really. It saves going through an awful lot of similar code everywhere. We get generated for us by T4, and that's one of the kind of great things about T4 templates is they can take a lot of the drudgery out. All we need to do is put a single line of text in our T4 template, and it builds a whole bunch of code for us. So these are the property events that we've got set up currently. We've got our command events, which are our buttons, and then we've got a helper function here, which actually does build that memory map as a dictionary of string and string. So what I have also got in the project, I've got an observable dictionary which I obtained from the web. There's full attribution in that file. I found when I used the observable dictionary that it's very, very slow. Early Dev, welcome to the stream. Good to see you. Have a salute from Alf. So yeah, so I've gone back to using the plain dictionary, and I think that's okay in this use case, just to use a dictionary. As I say, there isn't a two-way connection. All it is we update the display from our program. We don't update the values from our UI. I think we're going to be okay in that respect. So I thought what we could do is perhaps build a bit more of this for this application. So I've got kind of a roughly sketched out diagram in front of me. So I think what we'll do is look at some of the registers that we need to display. We're probably going to need to mess around with the size of some of this UI because it is a bit cramped, I think, to get all of the registers we need in. So let's go over to the CPU status user control. You see, all it is at the moment is is a label that says PC and a text box, and then it lives inside this stat panel. So let's make the XAML a bit more prominent. Please remind what a dictionary is. It has been VBA for the last few days. It's a key value. It's a collection of key value pairs, exactly. In this case, both the key and the value are strings. So that's why we have. That is why here we have. It's a generic dictionary, and the types are string, comma, string. So it could be int, an object. It could be, you can have any kind of combination of types in there, but we're just using a string pair. And all this stuff does here is display the bytes, which it's a U short and a byte. Display them as hex values, because of course they're being held as integers. The tuple is something slightly different. So the tuple, we're using a tuple in the disassembler. If I go back to that, early dev. So here's our disassembler. This is disassembling a single instruction, and basically we're using tuples here as a way of returning more than one thing from a method. So what we're saying here is, rather than returning some kind of object which you've created, so we could create an object which contains three properties, a U short, a string and a U short. Instead of doing that, what we've done is basically said, okay, we're going to have a tuple. It's going to have three components to it. We've named them, so it's rather than just saying it's going to return a U short, we send a U short, and we're going to know it as op address. A string, which we're going to know as op string, and a U short, which we know as next address. And then when we return, basically we return like this. So we've got our bracketed tuple or tuple, depends how you want to pronounce it. And then we've constructed a tuple, and that gets passed back. And then when we actually receive that as the return value from a method, which we do so here, we can deconstruct it. So we can deconstruct it into three completely different variable names. So we've got a variable name called ADDR, op, next ADDR, and we can then immediately use those. So it really is a really kind of a neat way of returning multiple results from a method without using an object, a custom object, and without using kind of out parameters. And I think in some cases, obviously I think 3 is probably getting to the limit of how many you want to return from a method, but it's a reasonable shorthand way of doing things. Yeah, it's pretty cool. I think it was introduced in C# 7, but it was one of the point releases, I think. So it may have been 7.1 or 7.2 or 7.3. I can't remember exactly when it came out, but yeah, it's useful for kind of as a shorthand way of returning multiple values. Okay, let's get back over to our XAML. So we've got a stat panel, which is stacked vertically, and then we've got a horizontal stat panel. So let's have a think. So what I'm going to do is I'm going to copy this stat panel and just one above here. So we've got another stat panel there, and we're going to have two. This is horizontal stat panel, so we're going to have two elements, two registered side by side. So what's the best way of doing this? Okay, I'm just going to go and check something in my Z80 class first. Let's go back up here. So I thought not. So at the moment we've got our registers. So these are 8-bit registers, obviously. So we've got A, B, C, etc. And then we've got our shadow registers. If you remember way back when we talked about the internal structure of the Z80 CPU, is that there are a set of registers and also some shadow registers. And there are special commands in the command set to swap these registers around. Study there, if you're going to do a TDD project, get used to TDD using NUnit. I'm using XUnit, but anything is good. Build around your understanding of C# structures rather than the particular project. And that's a good idea to get used to the idea. So I use TDD as a mindset rather than a shackle. So I do like to write my tests first, but I'm not always going to be able to do that on stream. So I'd say that 95% of the time we always write the tests first. So I don't want to become shackled into doing that. Okay, so what we could do with is also, rather than having these are the kind of pseudo 16-bit combined registers. So we've got HL, BC and DE. Kind of like to be able to have the accumulator A and the flag register as well. So I wonder how I can do that. Well, I think let's give it a go. We'll say it's a public U-short. I'll call it AF. And that's going to be given by we're going to cast into a U-short, which is obviously a 16-bit unsigned integer. We want F, and oops, I'm going to fool it to get the F in there, and then we want A. We want to shift that to the left by 8 bits. Now we've got a shadow register AF1 as well. So if we copy this, let's drop AF1 into place here. And that's the shadow version. And I'll just show you there's a diagram embedded in here, so we can just see this diagram. You can see we've got our main register set. These are 8-bit registers, but you can read them as a pair, 16-bit. And we get our alternate registers as well. And that's what these A prime are, our A1 registers. And then we've got an interrupt vector register, memory refresh, and then a bunch of 16-bit registers, IX, IY, stack pointer and program counter. We're going to display all those on our debugger. So we've got AF and AF1 now. Okay, so let's see if we can get AF and AF1 to display on our front end. So back over to the CPU status. So we're going to want to have we're going to call ACU flags and ACU flags 1 prime ACU flags. That's the accumulator and flags registers and kind of clumped together. So we'll give this a name. And we'll give a label. It will be AF, and the label here will be AF. And hopefully we get the prime in, I think, and the name will be AF and AF prime, or shadow AF, shadow. There we go. Okay, so that's under the front end part. So we can see we've got now 2 text boxes. There are labels here. Find that. So we need to kind of wire that up now. Yes, that was CodeRush feature, the embedded image in the comments. Yeah, I love to use those features. The images and the formulas, latex formulas are great for working with CodeRush. We need to wire these 2 values up now to our CPU, and we're going to use our T4 template to help us do that. So if we bring up the T4 template, I'm just going to do a bit of OCD kind of tidying up in here. We're going to create a couple of parameters, properties. The one was AQ flags. These are the bind values that we defined in our SAML. Flags prime, I think we called it, didn't we? Check that. AQ flags and AQ flags prime, that's right. So if we now go over here and we save that, so that's updated. As you can see, our generated view model over here has changed. So this is the generated file, and it's added these properties for us. So these are the partial properties that it's actually added for us. And the on-property change stuff is all done there for us. Okay, that's why it's quite fun having this T4 template concept. Okay. So we've done that, and over in our main window view model, we need to initialize these values. What we want to display them as is obviously the in hexadecimal. So yeah, if you're using multiple height, comment, text stuff, and colours the day to great effect, yeah, I really enjoy it. What you can do with making your comments larger and changing the colours. We want to make these values hexadecimal, so they're going to have to be strings. So if we say AQ flags, going to be and that's going to be our new value AF. Fine for the CPU, then AQ flags prime, going to be AF1. Okay, that's those properties added. Now we need to obviously handle the on-change notification. So we need to create a couple of methods. The partial methods here, and they're all basically very similar to what's above. This is going to be the on-change event or partial method for AQ flags. And this one for AQ flags prime. You'll know that if you've watched this stream. So this will be AF and AF1. So we can't set them like this, as you can see, which is a real shame. We can't set our values that way. So what we're going to need to do is to split this up. So what we're going to do first is we're going to take a var, we'll call it temp. So that's going to be the integer value that's coming back from this usual parse, where we're kind of saying it's a hex number we're going to be passing. And what we want to do then is to say the top half of that word is going to be register A. So we're going to say underscore CPU.A is going to equal. So what is it going to equal? Well, we want to take temp, and we want the top half of it. So we want to and that with FF00. Okay, we'll do that, and then we want to shift that to the right by 8 to get a single byte going to cast the whole lot to a byte. I think that should be correct. And then CPU F. F is going to be, I'll cast that as a byte as well, and it's simply going to be temp. And that's going to be ANDed with 00FF. And we want to cast the whole thing, rather than as a byte, flags, I believe. That can work. Let's get rid of that. There we are. So we've cast that as flags. We're going to do the same here. Move it down. And this is going to be A1, F1. So we need to figure out whether that's actually going to work. So let's run up our program and see. So we're hoping to see our flags and our accumulator. So that flag is going, it's not the individual flags we're going to see at this stage. We're just going to see the whole of the F register, so as a byte, basically, as a hexadecimal number. Let's see what happens when we run up our program. Okay, here we go. I'm just going to, and I appreciate it a bit more perhaps on the stream. So here's our registers, AF and AF prime. They started off in initial values of all zeros. Let's load a program in, and we'll load the arithmetic program in. And this is going to start at 0080. And what I want to eventually happen is that when we do that, we'll highlight the various rows in the disassembler and in the memory map. But I haven't quite got there yet. Here you can see this is the row we're going to be working with. We've got our program is loaded here, so it starts off 3E50. That's going to load the accumulator with the value of 5. So let's step and see what happens. So nothing happened. Okay, so the reason nothing happened is we're not actually updating our values. We've got our our link back sorted. Let's now go to the step function, the step method, and then we need to actually set them. We can actually go and borrow the code directly from here. Copy that down. So each time we step, we update our values. Okay, let's try that again now. Get over. I think doing that. If you can't see it, let me know and I'll try. I don't think I can make it any bigger. To be honest with you. At the moment, I don't seem to be having any effect, but we'll give it a go. Okay, let's load our program again. Arithmetic 1. That starts at 0080. And we'll just come down. There it is. So that's the row we're looking at, with our machine code program in it. This is going to add a couple of numbers and do some subtraction and whatever. And I think the answer is going to be 15 F in the end. So we're looking up here at our, this is the register we're interested in at the moment, the AF, and it's actually the first half of that is the accumulator, and the second half is the flags register, remember. And what we're going to have is going to display the flags as a set of individual bits at the top there. Let's step and see what happens. So hopefully we should load 5 into the accumulator, and we have. So we've got 5 in the accumulator now. Interesting enough, the shadow register's also got 5 in it, which this is wrong. I'm pretty sure that shouldn't have happened, but we'll check out why that's happened. I've made a mistake somewhere. Then we're going to do something else. What we're going to reload another register with a look at it, and then we're going to do an add. We added 5 and 10, and we've got 0F, which is 15 in our accumulator, and we've got 08, which is obviously some flags have been set. So that is actually working. So let's go and figure out why these are mirroring each other when they shouldn't be. So that looks okay. All that code looks okay, doesn't it? A1, F1. Okay, so that's correct. It looks prime. Oh, interesting. I wonder why my shadow flags are incremented at the same time. So what's going on over here? No, they're completely separate. Ah, here we are. This is the problem. We've actually got the wrong values here. It should be F1 and A1. That should sort that out. Let's give that a go. Once again, we're going to load the same program again. Another step, and this time only this AF register pair should actually increment. Oops. Increment at all. Oh, I didn't load, did I? Load that, and then we want to go to 0080. Making sure it's there. Yeah, there's the program. Another step. And it's only the AF register parent which is changing. That's good. Okay. So we really want to see what those flags are, don't we? I think that's probably the next thing we need to do. So over on CPU status, let's get another stack panel in place. So this time it's a slightly different arrangement we want. We're going to want to have 8 boxes across there. Maybe we could have it displayed as just binary. Not convinced. What's the best way of doing it? I wonder if we could have tick boxes. Potentially we could. Let's try it as just a set of flags for now. Let's get the stack panel going again. So this is going to be stack panel. And this is going to be an orientation that's vertical this time. We've got our vertically stacked panel. We want a label. So this is going to be interesting to think how it's best going to actually be presented. So let's try it like this. So let's have a label. And the label is going to have a content which is going to be just the letter S. Sign, that's the sign bit. We'll have a margin of 1 all the way round. That will allow us to adjust that. It's going to have a width. What's the width going to be? Let's say it's going to be, I don't know, 10. We can always change it, and a height of 10. Let's just leave it. Not have a height or width defined for now. So that's a label, and then directly underneath that we're going to want a text box. Let me just adjust this microphone. We want a text box. I think we could probably get away with having another user control this here, which could be means it could be a bit kind of neater to actually design this. But we'll start off this way, just getting one flag. This is going to be SignBit, bit 7. And it's going to have margin. Once again, 1, 1, 1, 1. So we can adjust it later. It's going to have a width 10. Vertical alignment is going to be centered. And the text is going to be bound. What's the best thing to call it? We'll call it SignBit, shall we? Oops. So binding. SignBit. So we got box and a box vertically above each other. So let's have a look at what that actually looks like when we run. Okay, so that's been I've actually centered the whole of the I actually want it over here, don't I? Okay, so let's adjust that. So the vertical alignment thing center needs to come out. Try again. Oops. Obviously not changed it. Why is that across there? Why is it not aligned vertically with the label? I can't follow that. That panel orientation vertical. Margin 1. Need a margin on here, don't we? Still decided to go and live over there. A horizontal alignment. No, it's over there, so it looks more like it. Give it a go and have a look. Yeah, so it's kind of in the right place now. We need to kind of float it across a bit. Okay, so let's give it margin of 5 point. So it's kind of sitting under the S now. So I'm just wondering what the best thing for that to be. If it was a tick box, it might be quite interesting. Box. the binding value of it. So what do we just check? Just checked binding value. I think. Nope, save that. We've got our hot reload working here, so now we've got, it's not quite wide enough, so we need to make it slightly wider. 15 wide. Now we need to move the S across slightly, so the S needs to go, I don't know, 3 perhaps? Yeah, so that's maybe even 4. Yeah, okay, that was good. Let's go and sort out the binding of that, and then maybe we can make this into a component. This kind of vertical stack here into a component. Okay, so once again to our T4 template, we want now to add the SignBit. So this is a property. We're going to say this is going to be a bool. We're going to call it SignFlag. See, what did I call it? SignBit. SignBit. Quotation marks around those, and then just make things line up nicely. Just because really. Save that. That's going to generate our partial class. Let's just stop the program running. So we now should have a generated view model, and we need to go and just tidy up our view model in the customizations we do in here. So we need to initialize our flags. So we're going to say SignBit equals, and then we're going to say CPU dot what's it called? Flags. It was S, wasn't it? And that is, we're just going to say equals 1. Okay, equals flag. Best way of doing this. We've got our flag register. It's there, and we've got a neat little check. We've got a little helper method down here, which is CheckFlag. Let's have the same method. Have the same methods. Yeah, I'll just, for now, I'm going to just pinch those methods. See if they fit neatly into the helper methods we've got over here. We don't need the alternate concept. Get rid of that. Same here. We don't need the concept of alternate. alternate flags. This is CPU. There. Okay. So we've got those logic items there. So here we should be able to say CheckFlag. Like that. Okay. So that's not going to be fine there. So let's get the same logic in our stepping. So flags down there, that bit, and then we want a SignBit changed method as well. So and we'll put it down here. Going to be SignBit, and I'm going to say this is not going to be a string, this is a bool. And what we're going to say here is so call it set flag flags s comma root. Spell flags correctly. I'll learn to spell flags eventually. The pudding, welcome. Coney Beard, welcome. Good to see you. So I didn't notice you there. There's a equals/equals character that can be used in C# now. Where's? Oh, I say a not equals. No, that's a ligature. So I'm using Cascadia Code as my font in well, I'll use it everywhere now. It's in Visual Studio and Visual Studio Code. As you can see, here's another ligature. We've got these. There's a kind of that's one character. Actually, it's two characters. I'm wrong there, but yeah, it's kind of a not equals, which is really nice. There you go, ligatures. So there's a fair few of them. One of the examples was that as a example. Just join them together, and these are actually kind of kerned closer together, and so it looks really nice. Yeah, so we got ligatures. The other thing is it's with the fat arrows. So we got any fat arrows in here. Oh, there we go. The fat arrows. You see, they're a nice ligature as well. Rather than equals and then the greater than, it actually looks like a fat arrow. Yeah, so that's Cascadia Code. Really recommend you check that out. You got to go to work. You're looking around. Okay, thank you very much, the pudding. I love your name, so I'll do it when you pop into stream. Okay, so we've got one flag in place. Let's go and do the rest of them. So this, I'm not sure if we can get away with having them as a individual user controls, but we probably put the whole bunch into user control, I think. Let's go over to our CPU status. So that's our vertical stat panel, and we need to wrap that now in a horizontal stat panel. And this is why I'm thinking we're going to pull this out, this whole kind of flag thing out as a user control. This is a horizontal stat panel. So we're going to wrap this little piece up in that stat panel, like that. And then what we're going to do is quickly go over to our to our Z80, and I'm quickly going to make a note of the order of the flags. And it shall be reverse order. So we've got the sign flag, the 0 flag, flag U is an unused flag, but we do need to know about it. The H flag, X flag, another unused flag, the parity flag, the negation flag, and then the carry flag. So that's the order we need to do. So let's create a user control. So we add a user control, and we're going to call it CPU flags. It'll take a few seconds to create that for us. We're going to change this to controls. We've got a grid there, so what we're going to do then is we're going to go into CPU status, and we're going to grab this little stack panel arrangement here, cut it out, and go to our CPU flags, and we're going to paste it in there. And then in our CPU status, we're going to this position here, we're going to insert control panel, control CPU flags, that there. It's going to have a squiggly underneath it, so it doesn't know anything about that. And I think all we need to do is to rebuild our solution, and it will know about it. And it now does. Okay, so our flag obviously has appeared way over here. We'll have to kind of see if that's a suitable place for it. We can adjust it then within our control. And what we've got now is we've kind of pulled out something which is going to be a bit big on our CPU status. Now we can just work in here. I should be able to shrink this down. And now it's basically, we do a bit of cut and pasta. So this is going to be the 0 flag, bit 6, the 0 bit, that, and copy another one. Is going to be bit 5. This is where the U bit. After that we've got the half carry flag. Half carry bit is bit 4. And then we've got X, flag X, bit 3, the X bit. Then we've got parity bit. Bit 2. And we call it parity overflow because it actually has dual function. And then we're going to have bit 1, which is going to be our N flag. This is negation bit. Finally, we're going to have our carry bit, bit 0. C, and this is the carry bit. So let's have a look at what that looks like in our UI. Okay, so that's nice. We've got our tick boxes that reach across there. We've got 2 Zs because I've not forgot to change one value, so let's go and sort that out. 2 sets. This should be a U. Okay. So now we need to go and do a bit of wiring up. So if we grab these, 1, 2, 3, 4, 5, 6, 7. We had a SignBit, we had a 0 bit. Now we had a U bit, and then we had a half carry bit. And then we had a X bit, parity bit, parity overflow bit, negation, and finally the carry bit. Let's go and tidy up the and there we go. If we save that, then once again we've now added up quite a few properties. That's going to go away and construct that partial class for us. Okay, all we need to do then is to just do a little bit of wiring up in our main view model. Okay, so we can simply go and do that. So if we copy this line of code, 1, 2, 3, 4, 5, 6, 7, and it's going to just 0 bit, the U bit, half carry bit, X bit, parity overflow, negation, carry, and this would be flag Z, flag U, flag H, flag X, P, N, and C. Okay, then we can copy those down to, now this is obviously looking like a method, isn't it? So we'll extract this into a method. Flags. Do the same what's up here. Okay, so we got that, and now we just need to do our change. What we do on a change. 1, 2, 3, 4, 5, 7. Let's quickly go through and do these. 0. And then like U, like that, half carry, H, what else we got, X, so having this T4 template does save you quite a lot of boilerplate. There's still a little bit, but far less than you'd have to do otherwise. It does make it for quite rapid UI development. Then there's negation, again, and finally the carry bit. Okay, well let's fire up our debug and see what happens. Okay, so now we've got our row of flags across the top there. Let's load a encode program and change the program counter to point at where that program starts, which is 80 hex. Exactly the same as before. So here's the program itself. Let's step through it and see if we can see our flags getting set. So we've got register pair AF, so the right hand pair of digits in AF register here represent this byte here as well, so we should see them change at the same time. So this is the row of program we're doing. So let's take the first instruction. So we're loading 05 into the accumulator, as you can see, and then we're going to step to the next command, which has loaded a value into different register. Now we're going to add those two values together. We're going to 05 and 0A together, so we should get 0F and we should get some flags set. So we got flag X set. So flag X, that's bit 3, that's a copy of bit 3 of the result that's in the accumulator. And if you think that 0F is 00001111, then bit 3 is indeed set, and so that's why the X flag is set. So let's step through the next. I can't remember what this does. Okay, so that's interesting. I can't remember what it does, but the half carry has been set there, and then we're going to step through the next command and the next one, and then we're just doing a subtraction. We're back to 15. So what we've done, I think what we did there was we doubled. The 15 was in 0F was in the accumulator. We doubled it to make 30, and now we've just taken 15 off it. That's why we've got the negation flag set, because we did a subtraction, and then the final command. I think we're probably at the end of it now. Yeah. So that is proving that our flags are being set up like that. So if we change the program counter now to 00F80 again, our flags are still set, but we can go and reset them to the correct values. But we can go and set all of our flags, yeah, and then we can step and see what happens. Oops. You can see they get cleared at that point when the flags change. So they're correct. That's pretty neat. I like that. Okay, so we seem to have a set of flags being shown. Now there's obviously more than those registers we've seen. There's also the other register pairs. So let's add those in. We can close CPU flags down now. We can go back to CPU status. Here, and all we need to do now is basically stack in all the other register pairs. So we've got AF, we want to do HL, BC and DE as our register pairs. Let me just grab this. So this time it's going to be H. Call it high-low. What should we call it? HL reg, HL pair, HL pair prime. This is going to be HL. Another HL. Prime and HL. Okay. Not sure why it's complaining about that. HL and Alt HL. Maybe that's the best naming convention. We'll do the next lot, which is going to be register pair BC, prime BC, BC pair, BC prime, Alt BC, and BC pair prime. Like that. And then we'll copy once more. Do DE. Prime DE. DE pair. And then DE. Not quite sure why it's complaining there. Let's see if it will build. Yeah, it's kind of complaining about that. Alt BC. What doesn't it like about that? It's okay about it now. Yeah, fair enough. Okay, that should build. And then back to our SQL templates, and we've got a bunch of properties to add. So these are going to be strings again. So I've already forgotten what the names were. So what are our bindings? HL pair and HL pair prime. So let's just add a whole load of those in. Prime, DE, prime, BC, prime. We had BC. Prime and then DE. Pair prime. Yep. Save. That will build our partial class again. And then over to our other part of the partial class, where we can start to set up the other part. So that was HL prime, or HL pair, HL pair, and that's going to be HL and HL1. Okay, we'll just copy that pair and do that twice more. Then we have BC, D, DE, E, WBC, and DE1. Okay. And what we can do then, of course, is copy that lot, those. We're going to keep the program counter separate just for now, because I might want to be using that in a slightly different way. So extract that into its own method. And we're going to call it set register pairs. Let's move that to the bottom of the file. Yeah. And then in our step, then simply call set register pairs. Like that. Okay, so time to test that again. Okay, so we're going to load in the same program. Here it is. At the program counter. Where's the program counter gone? Have I managed to guess the program counter? It's a bit off the bottom. Great, isn't it? There it is. Okay, so we need to make this whole box taller. So the program counter needs to go at 0080, like that, and then we can step. The 5 gets loaded into the accumulator. I expect the 0A to be loaded into a different register, and it goes into B. See, 0A gets loaded into there. Okay, and then we're going to step. Then we're going to double the accumulator. We're going to add the accumulator itself, so we should get 1E, which we do, 1E there. And then we're going to subtract. We're going to load 0F into C. We've done there. And we're going to subtract C from the accumulator and go back to 0F. And that's basically the end of our program. So that seems to be working quite well. I'd like these to be centered a bit. This text to be centered, but other than that, that's pretty good. So we should be able to also go and change the values. So if we go back to 0080 and we step, we got 5 in there. If we change that to 0A, okay, and then we step again, we can change these to 0. We step next, we're going to load A into there. Now we're going to add A and A together. We should get 1, 4, which we do. So we're actually able to interact and change the values in our registers through our debugger, which is what we want to be able to do. And we can also set the flags and things like that. So we've got now a kind of two-way connection through our debugger window. There's a few more registers we're probably going to need to add. So we need to add the index registers, IX and IY, and we're going to need to add some kind of theoretical registers, one called mempointer, one called Q, and also we need the interrupt and refresh registers and the interrupt mode. But that's probably enough for today, I think. So let's just quickly make the size of our main window a bit larger because it's too short at the moment. So we're going to say that the height is going to be 600, I think. I should get used to using this hot reload. That's really good. So we've got a bit more space here now. And what I've done, I've used I'll just show you this actually. For the columns, I've used this kind of star notation here to say this is like 75% of the width and that's 25% of the width. Once again, 60%, 25% and 10% for the kind of UI design. So it's kind of maintaining that ratio. The other thing interesting is when I click on a row here, the kind of it's disappeared off here. So we actually need to make this wider as well. So let's have a look at the width. The width is currently 800. Let's make the width 1000. Reload. Let's restart it to make sure it starts off in the correct fashion. Now when I click on a row, it doesn't disappear. That's good. Okay, pretty neat. I'm quite liking the way this is working out. We may want to put a box around the whole the thing here. So can't remember what that's called. You can kind of box things up, can't you? Now what's that called? I used it in my my synthesizer. So let's go and have a look at some of the code in the synthesizer. D drive. I'm going to finish up the stream by doing a little bit of making the UI look a tiny little bit prettier. So synthesizer source here, and here's our XAML. I'll open to encode. It's opened up on a different screen, but that's okay. You don't really need to see it. So it's a group box. Okay. Let's see how that works. Group box. Let's see if we can put a group box around those flags to begin with, shall we? So that was the CPU flags. So if I say group box, like that. Let's see if we can just simply wrap it like that and see what happens. And there is a group box around it, indeed, there is. So let's see if we can center those flags. I don't know if you can see that group box, there's a very faint line around it basically. And we can actually put a heading in there, I believe. Title. Let's do that. We'll do that while the hot reload's going. So that's the group box. And then what properties have we got on there? We've got title. Name. Should have kept that. Let's see if we can get code back up again. It was header. I probably never have guessed that. The header equals flags. And can we then say horizontal alignment into their center in that stat panel? Is that going to have the effect we want? Have a look. Yes, it's kind of centered that row of flags. We've got flags there. Let's make that bold. So let's change the font weight of our group box. Bold. Okay. Have a look at that. Yeah, that's quite nice. Wish there was a little less gap, so let's remove the margin, which is, there's only a tiny margin, so I think that might be the bottom margin. So that wants to be 1. We want, maybe that's it. Yeah. Oh no. Okay, so that has moved up slightly, hasn't it? So that's what we want to do to all of them. So it's a tiny amount though. I wonder if we have a negative margin. gone up quite a bit. Let's say -5. Yeah, that's nice. -5. So 0 on the end. -5 here. And we could probably do this with some kind of styling, but I've not really done styling in XAML yet. So that'll be something someone can teach me about. If you want to do a pull request to do something like that, or to introduce some new concepts so I don't really know about with XAML yet, then do feel free to do so. I do like this hot reload, that's very good. So now we've got the flags a bit closer to their labels. And we've got our flags here, so those could do with being kind of aligned. Not sure, because quite like they just need to move across a bit, I think. So each row here needs to have some margin to push it across. So that's flags. Let's go over to CPU status. We've got these stat panels here. So our text box could do with having a margin of say 10. That's the very first one. So let's put 10 in there and see what that does. Yeah, it could go quite a bit further actually, couldn't it? Maybe 30. 30. Yes. That's good. Like that, 30 and 30 then. Nope, not there. Yeah. 30. And here. And then the program counter needs to go across as well. The program counter here. Oh. 30 as well. We've got plenty of other edges to add, but you've seen me add plenty of them now, with no point in going to on stream and doing the rest of them. Okay, so I think that looks quite neat. Let's see what happens when we resize. Obviously we lose it when we get that size, but we're not going to be trying to debug with something that big. I'm not sure how to make things responsive actually in XAML. Probably is a way of doing it. No, it looks pretty good. Okay, I think what we'll do is call that a day. Stop. So it's been a relatively short stream today, and it's an impromptu stream because I'm not going to be able to stream tomorrow. I normally stream about 4 o'clock on a Wednesday. Today I was about 20 minutes late because I had authentication problems with OBS getting to Twitch. So it's been quite short, probably about an hour and a half, isn't it? We've been going just over an hour, nearly an hour and 40 minutes. So let's see if there's anyone out there to raid, shall we? First, before we do that, what we'll do is to commit this to Git. So we'll say added flags and register pairs to UI for debugger. Commit that. Let's sync that up to GitHub. So all the code is up on GitHub. If you want to check it out, you're completely welcome to do so. It's all on open source under an MIT license. If you want to clone the code, fork it and do PRs, you're welcome to. If you want to just claim the code as your own and use it as you will, then I don't really mind. It's all about learning together about this kind of stuff, so I don't mind what you do with the code. The idea of the project is that we will have a Z80 emulation, which will be a NuGet package, which I'll make publicly available. People will be able to download that and have a accurately emulated Z80 CPU in software. Once we've done that part, then we'll kind of try and actually emulate a real machine. Currently, I'm thinking along the lines of an Amstrad CPC. It could be a ZX Spectrum. It could be something else that uses Z80 inside it. It could be a Game Boy. It could be loads of things. I'm not really interested in particularly doing games with it, to be honest with you. But I would like to get a disk operating system like CPM running with the emulator. That's kind of the ultimate goal. There's still a long way to go yet, because we haven't got anywhere near all of the opcodes coded yet. There are many hundreds of them, and we might have 100, 120, something like that done. Each of which has to be kind of written and tested, and you have to write the tests first, of course. So, and then we've got a set of validation tests. We've got about 1,300 pre-written validation tests, which we're going to have to run. We have to get it so we can run them, and then debug the failures. That's going to take quite a long time. So this is a bit of a diversion into a bit of UI work, and having a debugger which we can run with our emulator rather than having to worry about using something like WinApe or another emulator. Because ultimately we want to use our software, not somebody else's, and then that way we can find out where the issues are. Okay, let's go over to Twitch and we'll see if we can find someone to raid. One thing I did want to show you, if you didn't see our stream yesterday, we did a very interesting little stream yesterday, which was to do with shaders, and I'll show you what we worked on, because I think it's tremendous fun. So this is CodeLife, the IDE, and this is the shader that we built. Let's see if it will run. There we go. Here comes Alf on the end of a rocket, and I really enjoyed making that with Morton yesterday. So that's available currently on demand under Twitch, and has also just been published to YouTube. So that's all done in about 120 lines of GLSL, and it's all generated mathematically. The only kind of thing that's a texture in there is a random noise texture. So all these flames, smoke, and all the variations in colour, texture, that's all done through mathematics. There's no polygons. This is a shader, and this is going to eventually be a kind of a feature on the stream. When we get raided, we're going to have Alf kind of blast across the screen like this on his rocket. I thought you'd like to see that. If you missed yesterday's stream, just check that out. And we'll be revisiting that shader next week, next Monday, to finish it off and get it into a web page that we can then use as a browser source in our channel. Okay, so let's go and see if anyone's around we can raid. Oh, we've got Copper Beardies, seems to be still on in our channel. Okay, so let's go and raid Copper Beardies. Okay, so let's go and see if anyone's around we can raid. He's actually on. We've got Copper Beardies. So let's see if he really is there. I don't think he is. Copper. Sometimes it tells you people are there and they're not really. So we're gonna go and raid. Oh, that's CLW. He's got no viewers at the moment, so let's go and try him. Okay, so thank you for joining this very kind of short stream today. It's in, as I say, it's in lieu of a stream tomorrow, because I can't do that due to work commitments. So take care, everyone. We'll see you next Monday for part 8 of our introduction to shaders, and we're going to be working on that shader I've just shown you with Alf blasting across the screen on the end of a rocket. And take care, everyone, and have a good weekend.